here's a different situation. I have a circuit that has a branch in it, okay, or like these two branching parts. And the letters here just mean we have a long bulb and a round bulb number 1 and round bulb number 2. So they're just different light bulbs. And I want to figure out the current in each light bulb. So I want to figure out the current in the long bulb, the current in round bulb number 1, the current in round bulb number 2. Which means, like last time, I'm applying the loop rule and the node rule to this circuit. But now I've got a more complicated situation, because what I've got to do is I've got to find the electric field in each of those bulbs. Okay? I can do that if I write out the loop rule and node rule equations, but how many equations am I going to need? How many different, we'll start with the loop rule, how many different round-trip paths are there in this circuit? How many paths can I possibly trace out that make a complete loop that go through the wires of the circuit? That's a good question. Do the paths have to go through the batteries? Do the paths have to go through the batteries? Does delta V round trip equal to 0 apply only to batteries, I guess is the question. It does not, does it? Okay, so 2 or 3, and so the question then becomes, does the path have to go through the battery, right? We can trace out one path that does go through the batteries. Let's say we start here, for example, and we go through battery number 1, and then we go through this wire, we go through battery number 2, and then we go through this wire. And then at this point we can do what? Either one, right? So let's pick the top one, right? So let's go through the top one and go through here. And we're back to where we started from, so that's one loop, right? So there's one. And then we can do the same thing, go through the batteries and get to here and then do what? Go down. Okay, so let's call that 2. And what's the third one? Around this loop, right? It does not have to go through the battery. We could pick a loop that goes through just those 2 light bulbs and their associated wires. So that would be loop 3. So in fact, there are 3 loop equations we could use with the loop rule. And let's actually write them out. We can just kind of reason out what the directions of the electric fields are. And by the way, what we often do in cases like this is that we looked last time, and we didn't get through the whole thing, but we asserted that. Remember, we had a problem last time. We had a thick wire and a thin wire. And you guys ended up calculating the electric field in the thin wire. But we also said that in the thin wire, the electric field was, how did the electric field in the thin wire compare to the electric field in the thick wire in this circuit? It was bigger, right? And in fact, in what is often the case in situations like this, the electric field in these thin, what are called resistors, right? Thin resistive elements of the circuit. The electric field is so much larger that the field in the thick connecting copper wires, highly conductive wires, it's very small. It's almost negligible. So that the potential differences across these wires are very small. And you actually did an experiment like this, right? You worked out the potential differences across different parts of a circuit element, and you found that across the connecting wires, the voltages were tiny, right? Like 0.01 volts, 0.00 millivolt range. So I'm going to go through and just worry about the wires. And I'll say this is, I don't know, let's call this E1. So my notation is going to be a little bit different from the picture here, but that's okay. Let's call that electric field E1, that electric field E2, and that electric field E3, and we'll call the length of this thin, usually tungsten in a incandescent bulb, this thin wire, call that L1, call this length L2, and call this length L3. And then this is EMF, and some EMF, and this is some EMF, so the total EMF would be 2 times that, okay? So give me an equation. What's the first loop rule equation going to look like? Okay, I have an EMF, and that's actually 2 EMF, right, because there's 2 batteries. So 2 EMF, and I go through the top. Okay, what's the sign? Minus, right, because I'm going in the direction of that field. So minus E2L2, and then what? Minus E1L1, and then equal to 0. Okay. What's loop number 2 going to look like? 2MF minus E3L3 minus E1L1 equals 0. Okay. What about the third loop, the one that just goes through the bulbs? Yeah. Okay. So let's pick a direction here. Let's say we're going. It doesn't matter, but let's say we're going in this direction. So we're going to go counterclockwise. So if I go counterclockwise through bulb number 3 here, I'm going opposite of the direction of the electric field, so that gives me a positive, right? So I have positive E3L3. But then if I go through here in the same direction as the electric field, that's a negative, right? So minus E2L2 equal to 0. Can I use those 3 equations to solve this system? There's 3 unknowns here, right? Electric field 1, electric field 2, electric field 3. Why not? One of the equations cancels out and we get the third one, right? These equations are not independent. If you could do this. You could subtract this equation, sort of both sides from this one. The EMS would go away. E1L1 would go away. And you'd be left with this third equation. Okay, so if you can get the third equation from the first 2, you don't have enough to solve the system. So what do we need? What else do we need in order to do this? Okay, well, if they gave us an answer, that would help, right? But where else can we get an equation from? What other rule can we use? Node rule, right? And how many different node rule equations are there? Independent, I guess, independent node rule equations, you could say. All right. Well, okay, I guess maybe we can phrase the question a little bit differently. How many independent node rule? I mean, you can write an infinite number of node rule equations, right? But how many independent node rule equations are there that can actually give you useful information, right? What node do we want to focus on? What particular useful node in this circuit would be the one that splits, right? Let's pick that spot, right? And so we know there that the current, the current electron current is going that way, right? So little I is going that way. So let's call, and again, I can sort of apply the node rule everywhere, and I know that along this branch of the circuit from the node rule that the current in this wire here has got to be equal to the current in this light bulb. So I'm just going to call this I1, okay? And it splits into 2 currents, right? That's got to be I2. And again, sort of another use of the node rule is again saying that the current here has got to be the current here. Okay, so the current through that light bulb is I2. And it's this current we'll call I3. It's the same as the current through this light bulb. So we end up getting I1 is equal to I2 plus I3. All right. And if I applied the node rule here, I would get the same relationship, just I2 plus I3 is equal to I1, okay, because the current I1 has got to be the same through a continuous branch, right? That's essentially another application of the current conservation, the node rule, okay? So maybe it was worded a little bit unclearly, but once we have a node rule equation, we can solve this system. Well, we've got to put this in terms of electric fields, right? So we have N A1 U E1 is equal to N A2 U E2. And I'm assuming that the N's and U's are the same for these light bulbs, and just the area is different. Plus N A2 U, or excuse me, N A3 U E3. So there's an equation with 3 unknowns. presumably we would have the other symbols. We'd have N, A, and U. There's an equation, or pick two of these, right? There's an equation and there's an equation. And so I'm not going to do it, but you could go through, just do a bunch of algebraic substitutions. It's just an algebra problem at this point, just going through substituting into a single equation so that you just have one unknown in a single equation, solving for it, and then plugging back in and getting a result. Okay, so you'll have a problem like this for homework, but this is the basic idea. You have to use the loop rule, but you also have to use the node rule in order to get enough independent equations to actually solve the system. And if you go into electrical engineering or some other circuits, take a circuits course, there'll be all sorts of more complex ways, different mathematical tricks of solving circuit problems, but they're all basically based on this. Okay, this is sort of the fundamental place where it's coming from. Okay.